All right, so I wanted to show you something to start out with. So under the Files tab, I put up this Figure Out Your Grade tool Excel file. So I made this hypothetical person. If you go to the grade section on Canvas, so you can see like how you scored on every single individual assignment. But if you go down here to the bottom, you can kind of see what your grade is for the online quizzes, SmartBook, Connect, and Excel categories, and then your kind of current 2 exams. So if we're looking at this Figure Out Your Grade tool, you would go through and you have a 72 in the Excel category, 88.18 in the Connect, 65 and 100 for the online quizzes and the SmartBook, and then you put your first 2 exam scores. Right? So don't put in your highest and lowest. These are kind of have formulas to automatically calculate so that you take your first 2 exam scores, and then you can start to play around with, well, what if I do really bad in the final? Well, this person would still end up with just over a C in the class, right? And then you can say, well, what do I need to get the B? If I get like the lowest possible A, actually probably there's like an 88 or an 89 that might still push this person over, but you can kind of play around with kind of different hypothetical final exam grades and what your final grade in the class would then be, okay? So that'll be kind of, I guess, I know you have other classes, other finals, they'll kind of help you, know how much effort, you're trying to, got a limited amount of time, how much time you might want to put towards this class, how fruitful it would be. So I've got that up there on Canvas. Also, if people have great questions, kind of figure it out using this. Everything should be up to date with the exception of that 5th Excel, which I'm hoping to kind of get a pretty good chunk of them graded this afternoon. Definitely by the end of the day tomorrow. Everything should be kind of graded up there on Canvas with the exception of that final. Okay. Yeah. Yep. So if you go to files, right, it's just been sitting up there all semester, right? So it's got the spring. So just under the files tab, just scroll down and it's just been sitting there all semester. So if you click on that, well, our final, oh, you're right. And I think our final, I don't want to get it wrong. I think this class is on Thursday, 9:45. My last section was on Wednesday. So Thursday, 9:45 in this classroom. We'll have 30 questions. So more than twice as long to take it. So timing really shouldn't be an issue. Those practice exams, very good representations of the types of problems that you'll see. I'll get the 5th Excel answer key up there this afternoon, which will also be some additional review of linear regression stuff. I would suggest, kind of looking over that answer key. That would be a good study tool for those linear regression questions as well. Obviously, you won't have to run the regressions on the exam, but kind of interpreting the output and using the output to answer questions. Okay. So before we kind of jump into doing some review, are there any questions not related to like specific problems or anything that you guys have before we jump into the review? Okay. Yeah. Is it like carbon factor and yeah, so right now everything other than the Excel, because I haven't had the 5th one, it's dropping the lowest. So what displays to you under that grades on at the very bottom on Canvas has your lowest of each type drop, and it eventually will for the Excel as well, and then the lowest 3 online quizzes dropped as well. Yep. Any other questions? So unless there's like specific questions, I'll probably work through practice exam B. I'll also kind of add in some questions that aren't on there that I think might be good things to know. But if there's someone's having a problem, we can kind of start out with those. So I'll just kind of start out with this problem 1. So we could answer this question. And actually, I did change this. Let me see. Let's see here. I'll mention some things. So I changed a few things from the one that downloads, and I'll kind of mention it along the way. So I changed the answer in part B here to be confidence intervals or hypothesis tests regarding sample coefficients, because we've got lots of different types of hypothesis testing confidence intervals we can do. So let's try to maybe, I guess, provide you something that might be a helpful study tool as you're going through. So anytime we're looking at the difference in sample means, and we're given some known population variances or known population standard deviations, either way, we said this was a scenario where we are using that standard normal or the z-tables. The only other types of examples where we use that standard normal or the z-tables is when we're looking at the difference in two population proportions. So the only time we use the standard normal or the z-tables is when we have known population variances with our sample means, or we have sample proportions. And I'll, as we work through these, I'll show you, like, I use the notation, right? So you should be able to kind of identify fairly easy. I'll use the word, but I'll also use the kind of notation. The other examples we had were differences in sample means, where we had sample variances, doing those matched pairs where we took the mean of the sample difference, we took the mean of our sample difference. And then the only other ones where we don't really look up p-values or build the confidence intervals, but I might expect you to know that we use the student t distribution is when we have coefficients and their associated standard variance. So 3 types of problems where we're using that distribution, and then 2 other types where we're using the standard normal or the z-tables. Okay. Any questions on this before we keep going? It's just kind of, I don't know, having it all in one place here to kind of keep it straight. But I'll also point out some things in the formula sheet that it reminds us. Okay. So this first one, right, we've got confidence intervals when we have unknown population variances. So we only have sample variances. Well, that was a situation where we are using the student t. The actual problem asks, when do we use the standard normal instead of the student t? So A is not right. We're looking at sample coefficients. That's the student t. And then if we're doing matched pairs, that's student t. So these first 3 are all student t. The only one that we would be using that z-table for is when we're looking at the difference in 2 population proportions. Go with that? All right, so for this first one, or I guess problem 2, we're looking at Indiana and Ohio. Indiana is our first group. We've got 40 people, and they've got a sample mean BMI of 28, and we have that sample variance as well. We've got the same thing for Ohio, right? That's our group 2. And then we want to build a 95% confidence interval for the true difference between the BMIs of both states. So we're going to go to our formula sheet. And we have the difference in sample means, but like I said earlier, I use the notation. So at the very least, like, look for formulas that have a similar notation, right? So here I've got S squared are my sample variances. So when I'm going to this formula sheet, I don't have sigma. I don't have the known population variances here. So here's my confidence interval and test statistic. If I knew the population variances, I don't. And it kind of reminds me, oh yeah, use the z-table. Right? That test statistic is a z-statistic. It comes from a standard normal distribution. Same kind of thing. I've got difference in proportions. Here's my confidence interval. Here's my test statistic. It's a z-statistic because I'm using the standard normal distribution. We go down here. I've got the difference in sample means. Okay, this is the one I want because I only had sample variances. Right? So here's my confidence interval equation. And then here's my test statistic equation for these types of examples as well. Now I have the degrees of freedom equation. I said you can punt on that. I'm not going to make you guys do that. I'll give you an assumed true degrees of freedom, which if we go back, I think it was 50 that I said. So really, all we do for these confidence intervals is we're plugging in the sample means we were given, plug in the sample variances and the sample sizes. The only thing left we would then need to do is look up how many standard deviations away, or what's that t value that I would need to go to get my lower and upper bound. Yep. So here, right, I guess it kind of trails off, but I gave you that assumed true degrees of freedom of 50. Yep. So I'm just going to write down kind of things that we have here, or we could just plug everything in. So if we looked at that formula sheet, it said take the first sample mean minus the second. Well, here, my first group was Indiana. So 28 minus 29. So we're going to build our confidence interval around that. The other information we were given was each group's sample variance. So Indiana was 9, and we had our sample size of 40. For Ohio, we had a variance of 16, and the sample size was 50. So our degrees of freedom, and I'll blow this up in a second, was 50. At the 95% confidence level, what would our alpha value be? Just, right? Alpha is the percent outside the interval in decimal form. So 95%, alpha would be 0.05. So if I'm just looking at these possible answers, the sample difference I found here was -1. So I should be building my confidence interval around that. So -1 should be smack dab in the middle of my confidence interval. If I'm looking at these and it's not in any of my confidence intervals, I could rule it out right away. Well, looks like -1 is in all of these. However, if I'm looking at this for B, -1 is a lot closer to the lower bound than it is to the upper bound, right? -1 is only what? About 0.48 away from -1.48, but 2.48 away from the upper bound. So it's not in the middle of my confidence interval. I could actually rule B out right away. Now, from there, I just need to look up that, where is it? T value, right? Now, remember, when we're looking up this value, we're going to go a certain number of standard deviations above and then below so that we have an alpha total outside the interval. If I've got two sides of my interval, that means I've got half of alpha on each side. So 0.05 over 2 is 0.025 at a degrees of freedom of 50. So go to my student T table. The area that I wanted on each side was 0.025. And I'm going to scroll down in this column to my degrees of freedom of 50. So the last thing that I needed, I now have. Now it's just a matter of getting this entered in to my calculator. Okay. So one thing to make that easier is maybe finding this ahead of time, right? And then you'll just have like one value to plug in there. You could enter it all in at one time. It just makes it a little bit more likely that you could make a mistake, right? Any questions on that? So I think what we end up with is our upper and lower bound would be this. So one thing I might add, a question that you might not see pop up on that practice exam, is, so this is the 95% confidence level. So with 95% confidence, can I say that Indiana has lower BMIs than Ohio? Well, if I've set this up as Indiana minus Ohio, some of the values for the true difference could be positive, which would imply that Indiana actually has higher BMI. Some of the values are negative, which would imply that Indiana's is lower. And in fact, one of the values is even 0, which would mean that they have exactly the same. So if my confidence interval crosses over 0, I really can't say anything about if one group is higher or lower. Now, maybe at the 90% level, I'd find a slightly smaller number of standard deviations. So let's just assume, I don't think this makes sense in terms of the numbers, but for the sake of this example, if I've only got negative values in my confidence interval, well, then at this level of confidence, and 90% confidence, I could say the true difference is negative, which would imply with 90% confidence, I can say Indiana has lower BMI, right? Because there's only negative values in my confidence interval. That makes sense. Any questions on that? So know how to make those interpretations. I'm probably telling you this for a reason. Know how to make those interpretations of the confidence interval. And really the key there is you're looking for, does it cross over 0? Questions there? All right. So the next one is going to ask us for a test statistic. And I give you an assumed true degrees. I already gave you that. I give you an assumed true, null, and alternate hypothesis. But I want to show you how you can identify what that is. Right? So if I wanted to test for whether or not Indiana has lower BMI than Ohio, how did I know that this was going to be the correct null alternative? So I could have added an additional question in there. So if I want to test for whether or not Indiana has lower BMI than Ohio, I think it helps to not just write this out as like the difference D. Like think about what we're actually doing. We're saying, okay, take Indiana minus Ohio. Right? That was our difference that we were looking at. If I want to test for whether Indiana has lower BMI, what has to be true about this difference? Yeah, if Indiana's is lower, then this has to be negative. Well, this is what I want to test for. So what I want to test for is always my alternative hypothesis. Now I could write that out slightly differently, right? So what I'm testing for here is that difference less than 0, which the null, I just assume the opposite is true, which is that it's greater than or equal to. So I think it's a little bit harder if I just try to start out here. But if I am writing out what that difference is, I think it's a little bit easier to see, oh yeah, if I want to know if Indiana's is lower, what I really want to find is this difference negative, right? Or less than 0. What I want to test for, that's my alternative hypothesis. I then assume the opposite is true for the null. So, and then usually if I ask you to identify the null alternative, the next question I would give you an assumed true one, right? Because if you got the null alternative wrong, you're going to get a lot of the other stuff wrong. So we start out here. If I've got a less than sign in my alternative hypothesis, I've got what type of tail test? Yeah, so we said less than sign, we've got a left tail test, right tail, or greater than sign, we have a right tail test, not equal to sign, we have a two tail test. So we're doing the left tail test. The question then asks, what's the test statistic? So I'll go to my formula sheet. We're dealing with these equations, right? We had only sample variances. Here's my test statistic. Right? Really, when we're calculating these tests, it's just a matter of plugging in our values. So we've got our sample means, we've got our sample variances, we've got our sample sizes. It's a matter of plugging those in and kind of making sure that we can get these entered into our calculator correctly. Now, one thing to help rule out some answers is every test statistic represents the number of standard deviations away we are from the assumed true value. Well, now that we're dealing with two population stuff, our assumed true value, I said to make it easier, it's always going to be 0. So this sample difference that we find, no matter if it's between sample means or sample proportions, that sign of that difference will represent the sign of our test statistic. Because if I see a difference that's positive, well, that's going to be a certain number of standard deviations above 0. If I see a sample difference that's negative, that's going to be a certain number of standard deviations below 0. So every single one of these test statistic equations, the denominator always represents a standard deviation. Well, variances and standard deviations are always positive, so the sign of my numerator tells me the sign of my test statistic. So if I plug things in here, let's see, so we got 28 minus 29. Let's see if I think it was what, 9 over 40 and 16 over 50. Well, this is always going to be positive, right? This represents the standard deviation for the difference in sample means. And here I found this sample difference was -1, remember? So my test statistic, right, should be negative. So when I'm looking at the possible answers here, I can rule out B and C right away, right? Because I know that my standard deviation is always, or my denominator of my standard deviation is always positive. So the sign of my numerator is the sign of my test statistic. And I found a -1 here in my numerator. So I think if I work this out, I end up getting -1.35. Okay. Once again, to get that correct formula too, like we had the sample variance, the S squared notation, we had the sample mean notation, kind of looking for those equations that have the same notation. At the very least is going to lead us to getting a smaller set of formulas that could be correct. Okay. Any questions on this one? All right, so the next one asks us for a critical value and a rejection decision. I changed some of the values from what the original Word document was for today's class because I want to show you a couple different things. Right? So I'm going to tell you what I changed. So here, instead of, I think this was -1.55, I changed it to -2.678. So assume that you found the test statistic was -2.678. And we've still got that same degrees of freedom, 50, and we're going to do a 95% confidence interval to find the critical value and the outcome of the test, being our rejection decision. So if we have a left-tailed test, our critical value is going to be the value that gives me that total alpha of 0.05 in the tail. But remember, whether or not we're using a student t or a standard normal, those are both centered at 0. My critical values for a left-tailed test should always be what? Yeah, left side of the distribution, so they're going to be negative. So, I'm using the student t-distribution. I want 0.05 in that lower tail. I have degrees of freedom of 50, so I can go to my student t-table. But if I look at these answers, do I really have to do anything for this problem? We just said our critical values have to be negative. There's only one value here that's negative. So knowing these principles sometimes can save you a lot of time and also kind of, allow you to, maybe not, oh, I'm not always gonna be this nice, but at least like rule out a few of them, right? Or at least one of them. So I've got kind of C, I know is gonna be the right answer here. But the reason, I'm gonna change things around a little bit here because here's my critical value, but this rejection decision was for the original assumed test statistic of negative 1.55. So we're actually gonna work through a little bit more. So the answer key is everything is correct, and it looks a little bit different than this, but I wanted to change some stuff to show you things that you could see on the exam. So we've got our critical value of negative 1.676, but if I've given you more options, how do I find that? So we'll go to that t-table, scroll up here. So the area that we wanted in the tail was 0.05. So that's going to be our column. We go down to 50, 1.676. Well, remember, the student t-table always looks at the right side of the distribution. We were looking at a left side. So it's going to be that exact same value because it's a symmetric distribution, but negative. So 1.676, our critical value is actually going to be negative 1.676, right? Because we got a left-tailed test. Excuse me. So if I wanted to then come up with my rejection region for a left-tailed test, it's going to be the area to the left. We were given that assumed true test statistic of negative 2.678, I think. So we'll just plot that in relation to our critical value. Well, negative 2.6 would be further into the tail. So that's very clearly in our rejection region here. I think doing this is the easiest way. That's visual and makes a lot more sense. If you really wanted to, what you could have done is if the absolute value of your critical value is less than the absolute value of your test statistic, this is when we reject, right? So the absolute value of my critical value, 1.676, absolute value of my test statistic, 2.678. Sure enough, it leads me to the same rejection decision as if I just drew the visual. But I don't know, to me, this is way easier. Any questions on that before we keep moving? All right, so I'm going to draw this on a separate one here, but let's instead say I wanted you to find the p-value. Okay, so maybe I ask you to find the p-value here. So the way that we find our p-value is we'll take our test statistic. So what was that? Negative 2.678. And for a left-tailed test, our p-value is going to be the area to the left. So if I ask you to find a p-value from the student t-table, we're going to have two issues. The first is, I look at this degrees of freedom of 50. There's only 6 values I can look up. So if it's not one of those 6 values, I can only put my p-value in a range. I said, I'm not going to make you guys do that. So if I ask you for a p-value when we're using the student t, you should be able to, the assumed true test statistic I give you will be one of these values in the table. So I think I gave you negative 2.678. So that's one of the values here. The problem is I have a negative 2.678. But it doesn't matter, right? Since it's a symmetric distribution. When I look up, and this isn't going to be part of the p-value, so I'll use a different color here. From the table, I can find positive 2.678, and the table will tell me the area to the right. Well, this is a symmetric distribution. So the area to the right of the positive value is the same as the area to the left of the negative value. So I can just look for this value and just remember, oh yeah, it's a symmetric distribution. So that 2.678, the area to the right of that would be 0.005. So, if this area is 0.005, this area would be the same. So that's my p-value, right? Just the area in that left tail. Now I drew this in. It's not like this really doesn't influence anything, but I was kind of just making the point. It's a symmetric distribution. So sometimes we're going to have to use that right side from the table, and just remember everything we would kind of apply to the left side in a similar fashion. Okay. Any questions? So we looked up a p-value. We can make our rejection decision there as well. We should kind of have this burned into our memory for the exam. We only reject if that p-value is less than alpha. Okay. So my p-value is 0.005. I think the alpha value is 0.05. So very clearly, very easily, we can reject the null here. Which, whoa, where did it go? Oh, here it is. Which was the exact same decision we made with the critical value approach, right? It was easily in our rejection region. Okay. Any questions on that before we keep moving here? All right. So the next set of questions. Scroll down here. We've got these proportions, and we're going to be looking for the difference in two sample proportions, US and Canadian gun ownership, kind of saying US here is group 1, Canada is group 2, right? And we want to build a 90% confidence interval for the difference between US and Canadian gun ownership. Right? So we're going to take in US minus Canadian. US is group 1, Canada is group 2. Same sample size from both countries, so that makes it kind of nice and easy. So if I'm looking at my formula sheet here, oh yeah, I've got these p hats. I've got these two sample proportions. Here's my set of equations. This first one being the confidence interval, right? Adding and subtracting at my upper and lower bound. And then here it was a little bit trickier with these proportions. We had to kind of do 2 steps to find this test statistic. Right? I guess you could technically do it as one if you plugged in p bar here, but that's a pretty nasty equation. So when it comes to finding the confidence interval, I'll probably go through this one a little bit quickly because we're just going to plug in the US's sample proportion everywhere we see p hat, Canada's sample proportion for group 2 here. We've got our sample sizes of 250. The only thing left we would need to do is look up that z value. So just a kind of a reminder of how we would do that, right? Let's see. What order do I want to do this in? So how would we do that? Well, now we're dealing with that z table. And I want to find the z value that would give me alpha total outside of my interval or alpha over 2 on each side of my interval. I believe it said the 90% confidence level. So my alpha would be 0.1 over 2, 0.05. So how do I find this number of standard deviations where I need to go? Well, I've got the area in the tail. So I'm going to go to my z table. I'm going to find 0.05. That was the area in the tail that I wanted. So I'm in between these two values. So negative 1.64 and negative 1.65. I'll use the higher of the two. And kind of remember, when I find this value, the negative and positive already built into my confidence interval equation. So it's really like that z value I need is just the 1.65. But you know, when I am finding the lower bound, I'm going that many standard deviations below to get the lower bound. Any questions how I looked that up? Now there's another way I could look this up, and I think it's easier. But if I go to that student T table, remember, if I want 0.05 in each tail, if I go to the very last row, this was like my benchmark standard normal values, right? So this very last row of the student T table actually gives me like these comparison standard normal values. So I can actually be a little more precise. Instead of 1.65, 1.645, right? So when I'm calculating these confidence intervals, I will use the last row. So I will use it out to 3 decimals, right? Now, the answers, even if you use the standard normal there, nothing's close enough to where like having to round the second decimal would lead you to answer, you know, select the an incorrect answer. But, you know, they might be off at like the 3rd decimal or 4th decimal. I usually only keep it to 3. I never go out any further than that. So also another thing I was going to point out here. So if I'm thinking about this formula, right, and I'm basing that confidence interval around whatever sample difference I found. Well, the US proportion was 0.32, Canadian was 0.26, so I found a positive difference. So of 0.06. So that should be smack dab in the middle of my confidence interval. So if I'm looking here, positive 0.06 isn't even in these confidence intervals. I can rule these out right away. Now, these ones are both plausible answers, so I actually have to work it out to figure out which one of these is correct. But I can make this a 50-50 shot, even if I just want to guess on this problem, just by knowing that. Is that any questions on that? Yeah. Yeah, so, right, we knew that we wanted the z-score, that we had half of alpha on each side, so 0.05. So you can do it two ways. The first way was you can use the z-table, right? We'll find the area that we wanted in the tail, which was 0.05, so we're in between these two. So 1.64, 1.65, we'll use the higher of the two. Or you can look up that area of 0.05 and use the very last row of the student t-table. Yep. Questions? So the next one, we've got given a null and alternative hypothesis, but let's think about if we wanted to identify it. So I'm asking about the test statistic and for whether or not gun ownership is higher in the US than in Canada, right? So how did I come up with this null and alternative hypothesis? Well, I'm thinking about the difference is US minus Canada. If I say I want to test for whether or not the US is greater than Canada, well, what would have to be true about this difference? The US is greater than Canada, this would be, yeah, greater than 0, positive. So whatever I want to test for, that's my alternative hypothesis. This is just the difference. So what I want to test for whether or not is the difference greater than 0. The null, I then assume the exact opposite is true, which is that it's less than or equal to. So that's how I would have identified the null alternative. What type of tailed test do I have here? Yeah, I got a greater than sign in the alternative hypothesis, so I have a right-tailed test. Okay. So now the next step is I need to find my test statistic. Okay. So if I look at my formula sheet, this is where I had to break it down into 2 steps. So I'm not going to write all this out. I'm just going to kind of explain it through and then kind of explain some of the principles that would allow you to rule out some answers. So you've got US was group 1. So US and Canada's proportions, you have their sample sizes. You could find P bar. You then plug P bar in to your denominator. You got your sample size of 250, and then you had your 2 sample proportions. These test statistics are really just a matter of getting those values plugged in, identifying the correct test statistic equation, which, like I said, here, I gave you the notation of P hat 1 and P hat 2. So kind of maybe trying to match up to a formula that has that in it. Okay. So one thing we can think about with these test statistics to rule answers out, as I said, the denominator always represents a standard deviation. Standard deviations are positive. So the sign of our numerator tells us the sign of our test statistic. Right? So here, my group 1 was the US, so it was 0.32. Canada's proportion was 0.26. So this numerator is positive 0.06. That sample difference is going to be a certain number of standard deviations above the assumed true difference of 0. So if my numerator is positive, that tells me my test statistic will also be positive. So if I'm looking at the answers here, I can rule out B, I can rule out B right away. Why does A look a little fishy? If I'm dealing with test statistics, they're telling me the number of standard deviations away, the sample difference I found was from 0. I found a sample difference of 0.06. How in the world is that 36 standard deviations away, right? That seems really, really high, right? Theoretically possible, but probably not likely, right? So I'm thinking it's probably C or D. If we actually plug everything in, I think you do end up kind of finding it is 1.47, which is a little bit more reasonable than 36. But once again, we could also rule out B there because we knew it couldn't be negative. We found a positive sample difference. So it has to be a certain number of standard deviations above the difference of 0. Why does maybe 1.96 look like a fishy test statistic? Maybe we're not super familiar, but if we're dealing with a standard normal distribution, 1.96 for a right-tailed test is often a critical value, right? because that's going to be a z-value that would give us exactly 0.025 in the tail. So like a two-tailed test will sometimes think. Now, task statistic still could be that, but a little bit fishy. So what I want to focus on more is breaking this 7 down. I'm going to break it down into a couple different pieces and add in some additional problems. So I'm giving you this assumed true test statistic, and we have that same right-tailed test. We want to find the p-value and make rejection decisions. I'm also going to show you how we would look up critical values, and then also, well, what if this was a two-tailed test instead? Okay. So we've got the actual problem was asking us for the p-value and the rejection decision. Okay. So we found a test statistic, or because it comes from a standard normal, we'll call it a z-statistic of 1.67. For a right-tailed test, the p-value is going to be this area to the right. Well, if I look up 1.67 in my z-table, it's going to tell me the area to the left. Well, I want the area to the right, so if I find the area to the left, what's the other thing that I need to do? Yeah, just subtract that from 1. So I'm going to look up 1.67 on my standard normal z-tables. So here's that second decimal, just because when I scroll down, I'm not be able to see it. So let me see. So 1.67, so 0.9525. Right? So that 0.9525 is going to be the area to the left. I'll subtract that from 1. And my p-value is 0.0475. Okay. Now, if I want to make my rejection decision, I could do it just at one level. So here, alpha was 0.05. We said we always reject when the p-value is less than alpha. So my p-value of 0.0475 is going to be less than 0.05. But I could do this for every level, right? So let me think about that. So if I've got my benchmark alphas of 0.1, 0.05, and 0.01, those correspond to what levels of significance? 10, 5, and 1%. And just to be complete, we usually don't talk about it in this way unless we're doing confidence intervals, but those would correspond to 90, 95, and 99% confidence levels. Right? So with my p-value of 0.0475, remember, we're checking to see, is that p-value less than alpha? So is it less than 0.1? Yep, so I can reject at the 10% significance level. Is it less than 0.05? Yep, so I can reject at the 5% significance level. It is not less than 0.01, so we would say we can't, we fail to reject, or we can't reject at that 1% significance level. So instead of just asking you to make a rejection decision at one level, I may ask you at which significance levels can you reject a null? So here, that would be the 10 and the 5% only. Okay. Any questions here before I keep going? So let me see. I'm going to do a couple things here. So hopefully I have enough room. Let's say instead I had done the critical value approach. Right? So for a right-tailed test, if I'd given you possible answers, what do you know has to be true about the critical values for a right-tailed test? Remember, both the standard normal and the student t are centered at 0. So if I want to find the critical value that gives me alpha, I think the alpha we had was 0.05, alpha total in that right tail, my critical value has to be positive. Right? So once again, I could use that Z table, but it's a little bit easier to just use that last row of my student T table. So I wanted 0.05 in that right tail. The last row would give me what that Z value would be. So 1.645. So here's my critical value for a right-tailed test. I draw that arrow in the right tail to get my kind of rejection region. Where does my test statistic fall? Well, my test statistic was 1.67. If I plotted that, that would actually just barely be in my rejection region. And that kind of matches up with the p-value approach, right? At that 5% level, we were just barely rejecting. Critical value approach at that 5% level, we're just barely rejecting. So both approaches will lead us to the same decision. Any questions on that? So what if this was a two-tailed test? Everything else is exactly the same, but it's a two-tailed test. There's only a little bit that we would have to do that's different. So if we wanted to find the p-value, once I find the area in this tail, for a two-tailed test, I have to remember, well, yeah, but it would have been equally as likely for me to see something that went against the null on the other side of the distribution. Because now things on the other side of the distribution go against the null, the two-tailed test. So I would take this area and do what? Find my p-value. Multiply by 2. Right? So this kind of shows that for a two-tailed test, it's always going to make my p-values larger, which means it's always going to be less likely I can reject the null. Two-tailed tests are much more difficult to reject the null because now, I only see evidence on one side, but I know it was equally as likely for me to see something that went against the null on the other side. So now if this was a two-tailed test, this is 0.095, what levels could I reject at? I rejected the 10% significance level, just barely, right? Could I rejected the 5%? No. So for that two-tailed test, I would only be able to reject at that 10% significance level. Okay. Questions here? What if I had wanted to find critical values for a two-tailed test? So this was our right-tailed test. What if I wanted to find the critical values if this was a two-tailed test? Well, for a two-tailed test, I'm now going to have a critical value or a threshold number of standard deviation cutoff on both sides, the same number of standard deviations, but one positive, one negative. So my critical values will now be the values that give me alpha total in the tails, which just like confidence intervals means I would have half of alpha in each tail. So if I keep that same alpha of 0.05 from the problem, if this was a two-tailed test, I now have 0.025 in each tail. And I think if we look that up, this is what I mentioned earlier, and I'll show you how to look it up in a second. Now I get positive and negative 1.96. And now if I plot that test statistic of, what was it? 1.67, my test statistic is no longer in my rejection region. So for a two-tailed test, I guess if I draw out the visual, right, I'm not in my rejection region now if this was a two-tailed test. Okay. Any questions on this? Okay. I think that's all I wanted to mention there. So like I said, I broke this down and kind of created some problems from this that weren't on there. If we just wanted to find the p-value of the rejection decision here, that was kind of 0.0475 when we rejected. And then I kind of just added more things in that, so you got a little bit of taste of a two-tailed test and finding critical values. Where are we at on time? So I want to point out a few things I think I failed to mention at the beginning. So when we were doing those, let me see if I can find it. Well, I'll just try to. So we were doing these problems up here where we had the only sample variances, the difference in sample means. I was giving you an assumed true degrees of freedom. But if we have these matched pairs examples, I think they're quite a bit easier, which is why I didn't start with them today. Because if we looked at their formulas, right, a lot less moving parts. But the degrees of freedom, I'm not going to give you an assumed true degrees of freedom in those because it goes back to simply being n-1 or the sample size -1. So anytime you see this D bar or these matched pairs examples, I don't give you like a degrees of freedom anywhere. Well, that's because if you have the sample size, all the degrees of freedom is the sample size -1. So if it's 81 is my sample size, degrees of freedom I would be using is 80. So If I don't give you an assumed 2 degrees of freedom, it probably means it's a matched pairs example here. Right? We did a lot of linear regression stuff last week. So there is some things that I wanted to mention about linear regression. Instead of working through problems, because we're kind of running out of time, giving you a set of things that you should know how to do. Okay, so I've already got these written down, but I'll kind of walk through. And these will be in the video. I'll post today's video too, so if you want to go back, but I'll make sure I clean this up. So we want to know how to interpret both a slope and an intercept coefficient from Excel output. So like I said, when I post that 5th Excel answer key, part A of both problems, I can't expect you to do. I'm not going to have you run the regression, right? We're not in a computer lab. But all the other parts could be turned into final exam questions, right? So interpreting slope coefficients, interpreting intercept coefficients. What should be the easiest problem on the exam is when I ask you to calculate a test statistic from linear regression output. Right? All you do is take that coefficient and divide it by that associated standard error from the Excel output. And that this equation is on the formula sheet as well, but right, that should be really easy. Okay. So this is given to you in Excel, this is given to you in Excel. We make rejection decisions the exact same way. We just look at the p-value that's associated with that coefficient or that variable slope coefficient. And if it's less than alpha, we can reject the null. If it's not, we fail to reject. Now remember, the null is that there's no relationship, or that slope is 0. Right? So if we can reject that, what we're really saying is we found evidence there is a relationship. Okay? So know how to make that reject. Hopefully, I mean, this applies to linear regression, but it applies to all of our other hypothesis testing stuff as well. Know what the R squared tells us or how to interpret it. Remember, that was like the proportion of the variation in our Y variable that we are explaining with all of those X variables that we put on the right-hand side. Okay. Know how to make predictions for your Y variable. So this was the examples where we walked through, we have this Excel output. So we would have, and I'll go back to this in a second. We would have every single coefficients estimate. So we would just be plugging these values in from Excel, right? We had all those values for the slope. So for instance, like if I was trying to make GPA predictions here, I had the slope coefficient and the intercept coefficient for each one of my variables. I would then plug that essentially into this linear regression equation. And then I would have to give you hypothetical values for this hypothetical person you're making a prediction for, right? So I would tell you, they had a SAT score of 1200. Let's look at, put some context to it. Maybe they had 5 years of education, 15 years of education, 5 years of experience. Maybe they were 34 and they were female. So this was a 1 if they're male, 0 if not. So this would have been 0, right? And then you would plug in the 34, 5, and whatever, 15 years of education. And then you basically just have this really long linear equation that you're putting into Excel. Okay? So that was that kind of 5th one I said to make sure you know how to do, which is make predictions. I think I got everything. Any questions related to the exam or? Yeah.
I got some questions.
Yeah.
Our classes exam is Thursday at 9:45, right?
I believe so. We pulled, that's what we said at the beginning of class, right? Here, we'll double check, but I believe it's, there we go. Thursday, 9:45. Yeah. So, yeah, so I've got, yep. And it reads as like practice exam A, Q 1 through 3, practice exam A, Q, and it should be at like towards the bottom of that playlist, right? Like today's will be, once I get that one, it'll probably be the latest one. But yeah, when I posted those last week, it should be towards the bottom of that playlist. Yep. All right. So if you do have any last minute questions and you want to meet sometime tomorrow, well, first of all, I'll be in my office from 2 to 3 today if you want to stop by, but I'll be around tomorrow. So send me an email if there's a time that works for you. If you want to meet, you have last minute questions. Or Wednesday, I have an exam in the morning. So Wednesday afternoon, I should be available as well. But for those, you'll have to send me an email to make sure that I am in my office when you show up at that exact time. Okay. So 30 questions, right? So 10 more questions, but twice as long. So time really shouldn't be an issue. Also, before you guys leave, one more favor can I ask of you guys? 4 or 5 today. I know you prove that I've been inundated with the emails for this as well, but if you can go on and do some evaluations for me, I greatly appreciate it. Helps me out, helps the College of Business out. And other than that, I'll see you guys Thursday morning. Thanks for a good semester and good luck with your studying.